Welcome to the Database Object Creation lesson, where we explore the basic building blocks of PostgreSQL. Today we will start by learning how to create the most fundamental building block, which is the database itself, how to create new schemas and how to work with different schemas within the same database, and of course how they differ to the database. And finally we're going to cover how to deal with tablespaces, what they are, how to use the default ones, and how to create new ones. Okay, let's start with the most fundamental object, the database itself. In PostgreSQL, creating a database is straightforward. You just type the command create database and define your database name. In this case, we're going to use the name schemas. This very simple command creates a new database called schemas, using all default settings. Think of it as creating a new empty warehouse for your online store's data. To run this command, let's connect this Postgres user to our local database, using PSQL as a database client. Once connected, we can just type the create database in the database name command. Did you notice that semicolon at the end of the instruction? This is to let the command interpreter know that we finished the command and it can now interpret and execute it. Once we learn more complex commands, we'll notice that it's better to break them into multiple lines. So end of lines are not necessarily the end of the instruction. The end of the instruction is a semicolon. So if you forget the semicolon and hit enter, you just need to add it. Do not repeat the command. But let's see what happens if we do. Let's try to create another database, for example CRM. So you type create database CRM, then hit enter without typing the semicolon. Notice that the character after the currently connected database, in this case Postgres, changed from equal sign to a dash sign. So imagine we thought that because we missed the semicolon, we needed to repeat the command, this time including the semicolon. Can you understand the error message? It says syntax highlight, at or near create, line 2 create database. And that's because the create command doesn't expect another create after the database name. We basically just said create database CRM twice. So the good advice now is always pay attention to this character after the connected database name. Only start a command when it's an equals. If it's a dash, that means that it's only waiting for a semicolon to run. However, you might haven't finished your command yet. For example, create database without the database name and enter, and then you see a dash. But if you just add the semicolon now, it runs, but gives an error because we haven't defined the database name. And that's because the character semicolon is not expected before the database name, so it just runs the command and then assume that you didn't want to provide a name. So to finally run the create database CRM command, in how many lines you want, just act like each new line was just a simple space. When creating a database, PostgreSQL offers several customization options through the with clause. There are so many options that we just can't exhaust them as of now. So let's break down the basic options. The option owner determines who has the administrative privileges to the database. The template defines that all database creations is a copy of a template database. The default template is template 1. Encoding sets the character encoding, in this case UTF-8, recommended for international support. Tablespace specify where the database files will be stored. And connection limit controls the maximum number of concurrent connections. We learned before that the \l command lists all databases. If you type \l followed by existing database name, you get some information about this database. Here we can see the database name, who the owner is, the default text encoding. So in our case it was UTF-8 that you should remember from the previous lesson. If you're on Windows, you should be seeing English United States.1252. To view more properties of your newly created database, add a plus to this command. For me, let me run a \x to enable expanded display. This is just to convert the output columns into rows, as I need to present this video with relatively bigger font size, so there's not much real estate for me to go too wide. So if you want to follow suit, remember that you can always type \x again to get out of the expanded display. To view even more properties, you can query a system table pg_database. Using the SQL command select, in this case star, all the fields, from PG database, where that name equals to schemas, within quotes. Because it's SQL command, don't forget to finish with a semicolon. like we saw before in the create database command. These outputs tell us important information about our database. The database uses UTF-8 encoding for character storage. It's owned by Postgres user. The default tablespace PG default is being used. We will explore access privileges and details in our last lesson of this section, Database Security Fundamentals, where we'll learn how to manage database permissions and user access. Remember, while the simple create database command is sufficient for many cases, understanding these additional options became crucial when deploying databases into production environments where specific character encodes or tablespace locations might be recommended or required. To connect to your new database, just type \c and the database name. Now you'll see your database name instead of Postgres. And that's because when you connected using PSQL command, you didn't specify the database name. So it established a connection to the database with the same name as your user. To disconnect and directly reconnect to your new database, just type \q to quit. Then re-enter with the command PSQL and the database name. In Postgres, every new database is created by copying an existing template database. By default, there are two template databases. Template 0 is a pristine template that never changes. Template 1 is a default template for new database. So you should think template 0 as your master blueprint and template 1 as your working blueprint that you can customize. To create a database from a specific template, you could have done create database, a database name, then template, and the template name. This time let's use template 0. You should remember that template 0 should never be modified, as it's the fallback for clean database creation. The template 1 can be customized with objects you want to have in every new database. When you create a database without specifying a template, it always goes to template 1. You can also create your own template database. For that, you can run the same create database command, set your database name, then use the isTemplate equals to true. Once a database is marked as a template, it cannot be dropped while there are databases created from it, and only super users can connect to it directly. Schemas in PostgreSQL function as namespaces that logically organize database objects. Think of schemas as different departments within a company, each with its own collection of resources, tables, views, functions, and etc. They can share names of resources in other departments without conflicts. By default, PostgreSQL creates all objects in the public schema, but using custom schemas helps organize your database objects and avoid naming conflicts. Postgres uses a search path variable to determine which schema to look in what priority order when an unqualified object name is used. The default search path is typically $user, which is a variable, in public, meaning that PostgreSQL first looks at the schema matching your username, then the public schema. To modify the search path, just type set search path and add the names of the schemas you have in the order that makes more sense to your business needs. There are a few important aspects to consider regarding the order of schemas in the search path. Number 1 is object resolution. When multiple schemas contain objects with identical names, the one in the schema listed first in the search path will be used. Second point is performance. If you have many schemas, setting a more specific schema path can improve performance by reducing the number of schemas PostgreSQL needs to go through. Then 3, object creation. When creating new objects without specifying a schema, PostgreSQL places them into the first valid schema listed in the search path. When I say in the first valid schema, I mean more than just existence. A schema is considered valid in the search path if 1. Of course, the schema exists in the database. 2. The current user has usage permission on that schema. If either condition fails, PostgreSQL silently skips that schema and continues to the next one in the search path. This is why the effective search path, what PostgreSQL actually uses, can differ from what's specified in the search path setting. Let me give you one example. If your search path is set to sales, user, and public, but you don't have usage permission on sales, PostgreSQL will silently ignore it, and your effective search path would only include public, assuming that user doesn't resolve to an existing accessible schema. Several common usage patterns for schemas include application-specific namespace. That's when you organize objects by application function like inventory, sales, and etc. 2. User private namespaces. This is when you create a schema for each user with the same name. And third-party application isolation. Placing third-party applications in separate schemas to avoid name collisions. Unlike databases, which are completely separate entities, schemas exist within the database and provide logical separation while still allowing access between schemas when needed. This makes schemas particularly interesting for implementing multi-tenancy, where multiple clients can use the same database structure but have their data isolated in different namespaces. Remember that schemas are not nested hierarchy. They exist at a single level within the database, with each schema containing various database objects. In Postgres, database and schemas serve different purposes in the data hierarchy. Understanding these distinctions is crucial for effective database design. Think of database as a complete application ecosystem, while schemas are likely different modules or components within that application. In our example of a large e-commerce platform, we might use a single database of multiple schemas to organize different aspects of its operations. So to summarize the key differences, in terms of isolation, databases are completely separate. You cannot query across databases. While schemas are logically separate, you can easily reference objects across the schemas. Regarding connections, databases require separate connection strings, while schemas are accessible within the same database connection. In terms of creation costs, databases have high overhead, new files, processes, and etc., while schemas have lower overhead, as they are just logical separation. Finally, databases are used to separate unrelated applications. Schemas are used to organize related components within an application. Schemas are particularly useful for avoiding naming conflicts and organize database objects by function or team responsibility. As a practical example of schema usage, create tables, products, and stock levels within schema inventory. Create tables, support tickets, and customer interactions in customer service schema. Create tables, daily sales metrics, and user engagement stats in analytics schema. And also create tables, invoices, and payment transaction in accounting schema. This organization separates functionality by purpose, allowing different teams to work on their respective areas without conflicting with others. It also simplifies permission management, as you can grant or restrict access at the schema level. By using schemas effectively, you can create a more organized and maintainable database structure, especially as your application grows in complexity. Unlike databases and schemas, which determine logical distribution of database objects, tablespaces define the physical data layout of your PostgreSQL instance. In other words, a tablespace is a directory in your file system that stores the actual data files containing your database objects. In PostgreSQL, tablespaces and databases have a many-to-many relationship. One tablespace can contain objects from multiple databases, and a single database can have its objects spread across multiple tablespaces. By the way, this is different from Oracle's approach, where a tablespace can only be used by one database. Think of tablespace as the physical where, and database or schemas as the logical what of your data organization. To create a new tablespace, use the command create tablespace, followed by the tablespace name. The mandatory component of this command is location, which specifies the directory where the tablespace data will be stored. There are some important aspects to highlight. The directory path must be absolute, not relative. The directory specified in location must exist and be empty. The PostgreSQL system user must have full read and write permissions on the specified directory. Tablespace names cannot begin with PG underscore, as these are reserved for system tablespace. Only super users can create tablespace, but ownership can be assigned to non-super users. An optional component of this command is owner, which specifies the PostgreSQL user who will own the tablespace. If omitted, the user executing the command becomes the owner. Tablespaces are particularly useful for managing disk spaces across multiple partitions or devices, optimizing performance by placing frequently accessed data on faster storage devices, separating different types of data, for example archive versus active, onto different storage tiers. However, it's important to note that creating tablespaces on the same file systems as the data directory or other tablespaces provides no real benefit and adds unnecessary complexity. PostgreSQL automatically creates two tablespaces during initialization. The first one is PG default. This is a default tablespaces for user data, and is used for the template 1 and template 0 databases. Consequently, it becomes the default tablespace for all new databases unless you specify otherwise. The second one is PG Global, that is used exclusively for shared system catalogs and global objects that are shared across all databases. These default tablespaces are located within the PostgreSQL data directory, also known as PostgreSQL cluster directory, which is basically the path specified via -d flag in the main process run. By the way, this -d flag can be suppressed in the presence of a PG data environment variable. To figure out where the running services cluster is, on Linux or Mac, just type PS for process status, with AUX option for more details. The filtering just lines with the word Postgres. So just look at the -d option. The actual cluster path varies depending on your installation method, but something like var, lib, PostgreSQL, version number, and main is a very common one. On Windows, a way of checking that is by running Windows R, the command services.msc. On the main services list, scroll to those starting with P and find something like PostgreSQL-x64-17 or any other version you're running, PostgreSQL server and the version. Right-click on it and then select Properties. You should be able to see the command pgctl.executable and the same -d option. To reveal it, you probably need to select and then drag to the right. Back to PSQL. You can run \db to describe existing tablespace. You should see the two default ones, however their location attributes should be empty. The PG default and PG global tablespaces show empty location values because they are special system tablespace that don't have explicit directory paths. These two tablespaces correspond to the fixed subdirectories within the PostgreSQL data directory. Respectively, PG default corresponds to the base subdirectory within the PostgreSQL cluster directory, and PG global corresponds to the global subdirectory within the same PostgreSQL cluster directory. In contrast, when you create a custom tablespace, you must specify an explicit directory path in the location parameter, which will then appear in the location field when querying PG tablespace or performing your \db. You can set different default tablespaces at various levels. The first one is at the database level, as you saw at the beginning in the create database command. You can specify a tablespace when creating a database, which becomes the default for all objects created within that database. For session level, you can set default tablespace parameter for all new objects created within the same session. Note that default tablespace setting only affects new objects created after it's set. Existing objects remain in the current tablespace unless you explicitly move them. Role user level. This works similarly to the session one, as it defines the default tablespace for all new objects created by that particular user. The ownership of a tablespace is separate from the ownership of the database object stored within it. When you create a tablespace, you become its owner unless you explicitly specify a different owner. Database objects like tables, indexes, and so on are owned by the role or user that creates them regardless of which tablespace they are stored in. The owner of a database object has all privileges on it, including the ability to drop it or grant access to other users. On the tablespace side, only a tablespace owner or super user can drop a tablespace, and it must be already empty of all database objects before it can be dropped. And that leads to the end of this lesson. Now you know how to create database with and without the definition of what physical tablespace the objects will be stored. You also know what schemas are, their purpose, how to create them, and the key differences they have from database. You finish with a deep dive into tablespace, the default ones, and how and why to create new ones.